Good morning, everyone. Can you hear me? Yeah, fine. Ignacio told us to already start. He grabbed coffee somewhere, but got stuck, I don't know, and should just join in a few minutes. So I would like to welcome you this morning for the session on the commercial ARD part, and I'm the first person to present. My name is Michael Riffler. I'm with GeoVille Information Systems. That's a privately owned company based in Austria, in the midst of the Alps, and we do a lot of, or let's say we are focusing on land monitoring based on high resolution and very high resolution imagery. We have not a focus on a particular sector or so, but rather are broad, providing solutions for different kind of sectors, meaning agriculture, urban applications, urban planning, but a lot of environmental stuff also. And we are heavily engaged in production for the high resolution layers, for example, within the Copernicus program. The solutions we built more or less covered most of the countries on the Earth. There's only a few gray spots, but our main focus is on. Just have to have a look. Is on Europe and Africa, so that's where we most of our things implemented. So from the title, I just saying combining HR and VHR imagery. This talk is not going to be about data fusion or so. I just want to tell you a little bit about our experiences with data we have when we apply HR and VHR based image analysis. So the three questions I have here for this workshop, what is an analysis-ready data set? So that's just the slides I want to go through for us as a service provider. So what makes it analysis-ready? What needs to be included to facilitate the data usage? And most importantly, what is necessary to accurately track changes in an efficient and automated manner, because that's in the end what land monitoring is about. In one of our projects we have together with Synergize and Brockman Consult is for the Sentinel-2 based global mosaic. We did a lot of analysis, or let's say for JRC, for whom we are actually running this project. The request was also to provide an analysis-ready data set. So we did some kind of research and looking into different definitions for analysis-ready data sets, and that's what is here stated from the Committee of Earth Observation Satellites Analysis-Ready Data for Land. And the main things they point out is that of course it needs to be processed to a minimum set of requirements, what we already discussed yesterday. It should allow immediate analysis with minimum effort from the user, and should also enable interoperability. And the minimum requirements are listed there, for example, to include general metadata, telling you about the history of the data, I think, which is very much, which is very important. Then quality metadata on a pixel and also data set level. This is very important, as I will show later on, to make informed decisions, so also to decide and select the data set. Then of course it requires measurement-based geophysical quantities, be it reflectance, backscatter temperature or whatever. Accurate geolocation is very important, and then for optical data, for example, also solar view angle correction and atmospheric correction. Just a few things. So in the next few slides I want to just go through a couple of samples and show issues we actually encountered. For example, here what is shown is a water and wetness probability index. So that's a product we actually derive to come up with wetland information. We did that, for example, we produced that for the entire continent of Europe, but also have a project running in Africa where this is very much used. And it's a combination of Sentinel-1 CSAR imagery and optical Sentinel-2 MSI imagery, and can also ingest Landsat imagery. And what I just want to stress here is if you have a look here to the picture on the left-hand side, that's a wetland area in the northeastern part of Lake Victoria in Africa, at the boundary between Uganda and Kenya. And overall, I think we try to leverage the full data sets from both Sentinel-1 and Sentinel-2, meaning that's a few hundreds of images, to come up with this nice map. And you see the features, so the darker the color, the higher is the likelihood that the surface is covered by water or wetness, and this can then be transferred into a user-specific classification. So in general, the wetlands are covered nicely, and I would say it doesn't matter, for example, if there is a if you have a slight error in geolocation accuracy of a pixel shift or so of 1 or 2 pixels, because the overall picture will just be fine. But for example, if we have a look on this lower rectangle here, area B, which is in detail shown here, for example, in order to track this small river, which is only like 20 to 30 meters, has a width of 20 to 30 meters, here it actually counts how accurately the geolocation of the data set is. So if you have a lot of imagery in that, which is not so nicely aligned, then of course this dilutes this information and you will not get this result. Another example is, for example, for damage assessment based on VHR imagery. So on the original image, so what we actually did here is a damage assessment based on 2 different time steps. Shown in the upper column is the original image from time step 1. It's the image from time step 1, and the second one is just an overlay showing time step 2. And you can see in the original image comparison that there's quite a distinct shift in the data. So it's several meters of shift. And then, of course, if you want to run an automated analysis, we have adjust for these errors, and that's what is done here in the corrected imagery. So this, therefore, again, I mean, additional computing effort is necessary before you can actually start with the analysis, and you also have to first have a look into the imagery and search for such distortions. And then, also, if I have a look on the specifications of the vendor, then I also have to question a little bit if design specification says you have a circular error on 90% of 12 meter, but you have imagery of sub-meter resolution, then I also have to question this a little bit, how useful this is in the end for the analysis. Another example, for example, for coastline detection, where we combine HR and VHR imagery. So here on the left column, you see a tiny stretch on the coast of Sao Tome, which is a small island west of Africa. And so that's the RGB image shown here in the left column, and then we have also a little bit of a more detail in the bottom shown for the red rectangle. The next column shows an index derived from Pleiades imagery, NDWI, based on 2.7 meter resolution, and then the next 2 columns from Sentinel-2B. Same index in the third column, and then another index based on 20 meter resolution also from Sentinel-2B, based on the visible and shortwave infrared. So what you try to do here is to leverage the best of the different data sources, meaning that, for example, if for initial detection, the 20 meter resolution data is best suited because it most distinctly shows the feature ocean compared to land. And then, of course, if we want to do like a hotspot analysis or going into more accurate analysis, we need to apply higher resolution imagery, and that's when we go to the left. What you can also see is that, I mean, in Sentinel-2B there is information in which better helps to make this distinction, and it will become more problematic, for example, here than for the Pleiades imagery. But as I said, if I do the combined image analysis, then I can first see, okay, where will the land-ocean interface approximately be, and then use the Pleiades imagery for the detailed analysis. However, again, we have this geolocation distortion shown here for on the left-hand side, the comparison between the Pleiades and just overlay Google Earth imagery, and then Pleiades versus Sentinel-2A in the right picture. And from this we see that we have a shift of 15 meter or so, Now 50 meters is not that much, but still it's a lot. For example, if you think about these houses which are located here along the coast and where you want to do, for example, a hotspot mapping, then it matters whether the coast has eroded 5 meters or so. And then if you have such a large offset in the data, then you cannot do such an accurate analysis. For example, for another region west of on the coast of Senegal, where you have tremendous changes along the coast, it doesn't in fact matter whether the data is shifted a little bit. So it always depends a little bit also on the context, on the analysis you want to do. And another example, for example, for construction site detection based on Sentinel-2 imagery, there's 2 examples shown here where we actually do a time series analysis. At the top line shows one example in the city of Innsbruck, and you can see that we have a quite nice time series here, and we can more or less accurately detect where the change happened. So that was, for example, for a bank who is interested in economic metrics based on the number of construction sites. For the second example, you see that there is a lot of noise in the data. So the values are going up and down, and of course I want to know for a particular point why is it going up, and in order to determine accurately determine when the change happened, it's necessary to know, for example, for a particular point, okay, why is it here higher? Did the construction already start or not? Because for the bank, it's very much important to know that more or less to 1 or 2 months, the onset, 1 or 2 months accurate timing. So in the end, I can say at the end of 2016, yeah, the construction for sure started, but yeah, as I said, so we want to know that in a more accurate manner. One last example is for detecting field parcels. That's also done on Sentinel-2 multi-temporal imagery, and Sentinel-2 imagery is very well suited for this kind of analysis. But what is very important that you actually have to filter the information, because if you have a lot of or let's say several images going into the algorithm containing problems, then of course this will mess up your field parcels. Especially if we think about these examples where, for example, the fields are only a few decameters wide. So there it's really critical in order to come up with a good algorithm, or let's also say stable algorithm, and not to mess up things with bad data quality. So therefore, we did a lot of work to extract information, because, for example, for Sentinel-2, there's already a lot of information is included about data quality, but it's just not as easy accessible. For example, if you run an analysis based on AWS, all the imagery can access in an easy way, but it's not that easy, for example, for this quality metadata information. So we were looking for all different kind of issues with the data. It's just listed here on the left-hand side. It's here the kind of issues which are actually in the data, and then, for example, whether this is an issue for level 2A or within the level 1C data. So don't want to go into the detail with this table, just to show that there's quite some potential issues in the data, and then you have to decide on a product basis whether this issue is relevant for your solution. There might be certain issues which are irrelevant, but for others this is not the case. And so that's what I wanted to say here. What is a potential issue? Well, pretty much depends on the solution. Another thing is that where to find this information. For example, in the metadata of Sentinel-2, you find different quality flags on the geometric quality, sensor quality, general quality, format correctness, and so on. But the question is, what's behind these quality flags? And that's not so easy to find out. So you have to find the relevant documents where you see what these checks all include. And that's just another point, so which is very important, is the documentation of the product, and that this documentation is easily accessible for users. So just a little bit of analysis about this metadata information. So we actually install the database, and you can now query this and then see, for example, that for Sentinel-2A and Sentinel-2B Level 1C imagery, the percentage of failed imagery is approximately the same. So roughly 5% of the data has issues, and the same is true for the Level 2A imagery. So we can do that also, just show a little bit time dependent, and that's what's shown here, the failed data percentage for a particular month. Starting in the left top figure with the commissioning phase of Sentinel-2, of course, initially there were quite some issues, but then, of course, once the sensor got operational, issues decreased, and now we are more or less here on a stable range between 5–6% or so. There's this, I don't know what this wiggle in between means, but in general the data quality is quite stable. What is shown in the bottom figure is the failed percentage per UTM zone. So you can see that this is also more or less stable. So there's no geographic bias or so in the data. What is a little bit more astonishing is this cloud cover percentage, also extracted from the database, is that we have this this uneven distribution. So we have a high percentage of 0 to 10% cloudiness and 90 to 100, and then of course low values in between. So I think this information is a little bit questionable, because I would expect a more even distribution about the cloudiness. Then we also did some comparison for the inter-satellite operability, so Sentinel-2A, 2B co-registration, and I think around end 2017, early 2018, there were some issues in the co-registration procedure, and so what we did here is for a couple of tiles to compare the image shift. So what you can see on the right-hand side is the different shift patterns, where it shifted to the northwest, north, northeast, and so on, and then color-coded that for the different tiles. And you can see for most of the tiles, there is this shift pattern tends towards a northward shift of the data. So this is also, if you want to combine the data sets, of course, this is also something which is very much relevant. Finally, also something which has already been addressed yesterday is cloud masking. Shown here is the center core cloud mask in the left for different, if you select different cloud probabilities. So the upper row means the low probability clouds, and then for the three different cases in the columns. The middle is the medium probability clouds, and below is the high probability clouds. So in general, you can see, for example, if you choose the high probability clouds, you will be fine for most cases. Just on the lower left, you will see that there is also some clouds and shadows are missed with the high probability. For example, if you choose the low probability clouds, then you will also see that, for example, in the middle column, there is a lot of urban areas is actually covered or is masked as clouds, and that's what's also shown on the upper right, for example, where we have this inset urban area, where most of the area is covered by low or medium probability clouds. So if you want to run, of course, some urban applications or provide an urban solution, this is an issue, and so where you have to find a solution how to work with this data. We found a way around where we actually include all the information, but do some weighting based on the cloud information, and this works smoothly, but it's always depending on the kind of solution you actually have. And maybe some not so nice example down is a VHR-based cloud mask or for VHR imagery, where not only so it shows that this cloud mask has been produced manually, and what is also bad is that quite some clouds are actually missed, so this is also some kind of poor information provided by the vendor. So in order to facilitate the data usage, then we established a service, API service, where you can actually query the data. Has just recently been developed and needs to be further extended. But in fact, what it provides is that, for example, for certain criteria, it provides a blacklist of data which should not be used for the analysis, and this facilitates the data usage a lot for us. Finally, another also very nice and important service is here, for example, the number of observations for Sentinel-2A for the year 2017. And shown on the left column is the total number of observations. Then in the middle is the total cloud-free observations. On the right, the average data gap you have for Sentinel-2A. So for us, for example, if we know that we have to develop a particular application, then we exactly know where we have to go to test a new algorithm. For example, I will go in and then also I don't get that with this pointer, with this mouse. Then, for example, that I not only select here an area where I have very dense observations, but of course will particular focus on the area, for example, along the boundaries to exclude artifacts if I do a product rollout, or for example, or also, for example, then here taking into account cloud-free observations. Then, of course, this is very nice that you can actually really go to problematic areas to test your algorithms. And what is also interesting then to see, for example, the average gaps. So although you have like 3-day observation frequency in Europe, for Sentinel-2A it was like 5 days, I think, between 5 to 10 days. You see that the average observation time can be much larger. So this can be up to 15 to 20 days, and we also have, for example, a product analyzing the maximum data gap, which can be 70 to 80 days, just due to clouds. So I come to my summary. What is important for us as a service provider in terms of ARD requirements? Most of all, I think what is very important is documentation, so that you can really go into the documentation, also see how the data has been processed and extract information. For example, what I mentioned before with this particular quality flag, so what's in these tests. Then, of course, we would also wish to have the general access to the general metadata, so on dataset and pixel level, to quality metadata. Of course, we also work on geophysical quantities, want to have the positional high accuracy, so sub-pixel accuracy. It's very helpful to have a good cloud mask, but there's not the one and single solution. So one has strengths in particular areas and weaknesses in others, and so it is true for others as well. What for us is rather optional feature is atmospheric correction. Although it's very highly appreciated, if you have that available, it can also mess up other things. So would rather like to have like an option saying, okay, here I need it, and for other type of analysis I don't need it. And then also, for example, this atmospheric intercomparison experiment has shown that the results are quite different. And what is also very important for us, I would say, is API-based data access, so that we can have data access by the machines. Thank you for your attention.
Thanks for that very interesting talk about all the problems you encountered. We have time for one quick question, if anyone has any. Oh.
So I was kind of interested by this kind of bimodal distribution and percent of cloud cover that you saw. You said that was weird and unexpected, and I agree. Right? Do you have do you think it's because the reported fraction is being overestimated or underestimated in some way? Or you said it was unexpected.
Do you have an answer for that, Miha?
Yeah, it happens when you have large areas covered by cloud and large areas not covered by cloud. And you split this into little squares. Most of the squares will be either fully covered or fully not covered, and there will be a small number of squares on the boundary. So this is somewhat expected.
Yeah, but I wouldn't expect, so I mean, this analysis has been run on a Sentinel-2 tile basis. So that means 100 by 100 100 by 100 kilometer. And I mean, for synoptic systems, there should be something, so I wouldn't expect that, you know, that it would cover a full, just a full tile would be covered or not covered cloud-free. So I think this is not, that's not a physical behavior. We just explored that last week on Thursday, I think, before I traveled to this workshop. So we really have to have a look really what this is about. But I have the impression that it's not natural. It's somehow it's weird.
Great. Thank you very much.